After the conductors to all the electrodes except the ground rods are cut, the first building is not any less safe or less protected from transients and surges. The ground rods alone provide sufficient grounding in this case. The purpose of a grounding system is to provide a low resistance path to earth for fault currents and lightning strikes. The more electrodes connected to the system, the lower the overall resistance. However, once the resistance is low enough to meet the code requirements, additional electrodes provide diminishing returns in terms of safety. In the case of the first building, the ground rods alone provide a resistance that is below the required threshold. Therefore, the removal of the other electrodes does not significantly deteriorate the grounding system's ability to protect the structure. The 11 amps current flowing on the electrode system before the conductors were cut off could be considered objectionable. However, the subsequent drop to 0.75 amps after the removal of the other electrodes is a significant improvement. High levels of ground current can indicate faulty equipment, insulation breakdown, or other electrical issues. In this case, the reduction in current after removing the additional electrode suggests that the fault or issue has been resolved. Based on these thought experiments, it is reasonable to conclude that the code requirement for multiple electrodes is not necessary for all structures, as a single ground rod system can provide sufficient grounding under certain conditions. The decision of whether to use additional electrodes should be made on a case-by-case basis, taking into account factors such as the number and type of electrodes present, the measured ground resistance, and the presence of objectionable current. A grounding electrode system, also known as a grounding system, is a crucial component of electrical safety. Its primary function is to provide a low impedance path for fault currents to return to the source, thereby facilitating the operation of overcurrent protection devices such as circuit breakers or fuses. This system also plays a vital role in dissipating static electricity and providing a reference point for voltage stabilization, protecting equipment and personnel from electrical hazards. The main components of a grounding electrode system include the grounding electrode, the grounding electrode conductor, and the bonding jumpers. The grounding electrode is the physical connection to the earth, typically a ground rod, ground plate, or underground metallic water pipe. The grounding electrode conductor connects the grounding electrode to the electrical system's grounded conductor, usually at the service entrance. Bonding jumpers ensure electrical continuity between metallic parts of the electrical system, such as metal conduits, enclosures, and equipment grounding conductors. The code establishes minimum requirements for grounding electrode systems to ensure electrical safety. These requirements vary depending on the type of structure, the size of the electrical system, and the local soil conditions. Generally, the code specifies the types of grounding electrodes that are permitted, the minimum size of the grounding electrode conductor, and the maximum allowable resistance to ground. The purpose of these requirements is to provide a reliable and effective grounding path that can safely handle fault currents and protect against electrical shock hazards. The grounding electrode system provides a low impedance path for fault currents, allowing overcurrent protection devices to quickly trip and de-energize the circuit. This minimizes the duration of the fault and reduces the risk of electrical shock or fire. It helps to stabilize the voltage in the electrical system, reducing voltage fluctuations and improving the performance of sensitive electronic equipment. Additionally, it dissipates static electricity, preventing the buildup of static charges that can damage electronic components or cause electrostatic discharge (ESD) events. A single ground rod may be sufficient in certain circumstances, particularly when the soil resistivity is low and the required resistance to ground can be achieved with a single electrode. However, the code typically requires multiple electrodes when a single electrode does not meet the resistance requirements or when the system serves a large or critical load. Multiple electrodes provide redundancy and lower the overall resistance of the grounding system, improving its ability to handle fault currents and protect against electrical hazards. Factors influencing the choice of grounding electrodes include soil resistivity, which affects the resistance of the electrode to ground, the type of soil, which can impact the corrosion rate of the electrode, the available space for installation, which may limit the size or type of electrode that can be used, and the local code requirements, which specify the types of electrodes that are permitted and the minimum installation requirements. Ground resistance testing is performed to measure the resistance of the grounding electrode system to ground. This test verifies that the grounding system meets the code requirements and provides an effective path for fault currents. There are several methods for testing ground resistance, including the 3-point fall of potential method, the clamp on ground resistance meter method, and the 2-point method. The 3-point fall of potential method is the most accurate and widely used method. It involves driving two auxiliary electrodes into the ground and measuring the voltage drop and current flow between the grounding electrode and the auxiliary electrodes. The clamp on ground resistance meter method is a non-invasive method that uses a clamp on meter to measure the resistance of the grounding electrode without disconnecting it from the system. The 2-point method is a simple method that can be used for quick checks, but it is less accurate than the other methods. Proper grounding is essential for electrical safety. A properly installed and maintained grounding electrode system protects people and equipment from electrical hazards. It provides a low impedance path for fault currents, ensuring that overcurrent protection devices quickly trip and de-energize the circuit. It also stabilizes voltage, reduces voltage fluctuations, and dissipates static electricity. Regular inspection and testing of the grounding system are necessary to ensure that it is functioning properly and meets the code requirements. Grounding electrode systems are critical for protecting against lightning strikes. Lightning strikes can inject high surge currents into electrical systems, causing damage to equipment and posing a risk of fire or electrical shock. A properly designed grounding electrode system provides a low impedance path for lightning currents to flow to ground, dissipating the energy and minimizing the risk of damage. The grounding electrode system should be connected to all metallic parts of the structure, including metal roofs, gutters, and downspouts, to provide a comprehensive lightning protection system. Effective grounding is a critical component of surge protection. Surge protective devices (SPD) are used to protect sensitive electronic equipment from voltage surges caused by lightning strikes, utility switching, or other electrical disturbances. SPD diverts surge currents to ground, preventing them from reaching the protected equipment. The effectiveness of an SPD depends on the quality of the grounding electrode system. A low impedance grounding path is essential for the SPD to quickly and effectively divert surge currents to ground. The NEC requires all surge protective devices to be properly grounded to ensure their proper operation. When objectionable current is discovered on a grounding system, it should be investigated and addressed to eliminate the source of the current. Objectionable current is current that flows on the grounding system under normal operating conditions. It can be caused by faulty equipment, insulation breakdown, or improper wiring. Objectionable current can create a shock hazard and interfere with the proper operation of sensitive electronic equipment. The first step in addressing objectionable current is to identify the source of the current. This can be done by systematically disconnecting circuits and equipment until the current disappears. Once the source is identified, it should be repaired or replaced to eliminate the objectionable current. In some cases, it may be necessary to reconfigure the grounding system to minimize the flow of objectionable current. The requirements for grounding electrode systems can vary depending on the type of structure. For example, the grounding requirements for a residential dwelling are different from those for a commercial building or an industrial facility. Residential dwellings typically require a grounding electrode system consisting of a ground rod, ground plate, or underground metallic water pipe. Commercial buildings and industrial facilities may require more extensive grounding systems, including multiple ground rods, ground rings, or concrete encased electrodes. The specific requirements for each type of structure are outlined in the NEC and other applicable codes and standards. Regular inspection and maintenance are essential for ensuring the continued effectiveness of the grounding electrode system. Grounding electrodes and conductors should be inspected periodically for corrosion, damage, or loose connections. Ground resistance testing should be performed regularly to verify that the grounding system meets the code requirements. Any deficiencies should be promptly corrected to maintain the integrity of the grounding system and ensure electrical safety. It is important to maintain proper documentation of the grounding electrode system, including records of inspections, tests, and repairs. This documentation can be helpful for troubleshooting problems, verifying compliance with code requirements, and demonstrating due diligence in maintaining a safe electrical system. Documentation should include the type and location of grounding electrodes, the size and routing of grounding electrode conductors, and the results of ground resistance tests. The National Electrical Code, or NEC, provides detailed requirements for grounding electrode systems in Article 250. This article covers topics such as the types of grounding electrodes that are permitted, the minimum size of grounding electrode conductors, the methods for bonding metallic parts of the electrical system, and the requirements for ground resistance testing. Article 250 is regularly updated to reflect changes in technology and industry best practices. Staying up to date with the latest version of the NEC is essential for ensuring compliance with code requirements and maintaining a safe electrical system. Local amendments to the NEC may also apply, so it is important to check with the local electrical inspector for any additional requirements. Grounding electrode systems play a critical role in electrical safety. These systems protect people and equipment from electrical hazards by providing a low impedance path for fault currents, stabilizing voltage, and dissipating static electricity. Proper design, installation, and maintenance of grounding electrode systems are essential for ensuring electrical safety and compliance with code requirements. Regularly inspect and test grounding systems to ensure they are functioning properly. Promptly address any deficiencies to maintain the integrity of the grounding system and protect against electrical hazards. The grounding electrode conductor, or GEC, is a critical component of the grounding system, providing the connection between the grounding electrode and the electrical system's grounded conductor, typically at the service entrance. Its size is determined by the size of the service entrance conductors, as specified in NEC Table 250.66. The material is typically copper or aluminum, and it must be protected from physical damage. Proper installation of the GEC is crucial for ensuring a low impedance path for fault current. Bonding jumpers are used to connect metallic parts of the electrical system together, ensuring electrical continuity and providing a path for fault currents to flow back to the source. Bonding jumpers are required for metal conduits, enclosures, equipment grounding conductors, and other metallic components that could become energized during a fault. The size of bonding jumpers is determined by the size of the circuit conductors, as specified in NEC Table 250.102 colon. The material is typically copper or aluminum, and it must be protected from physical damage. The purpose of bonding jumpers is to create an equipotential plane, minimizing the voltage difference between metallic parts of the electrical system and reducing the risk of electrical shock. The concrete encased electrode, or U for ground, is a type of grounding electrode that consists of a bare copper conductor encased in concrete. It is typically installed in the footing or foundation of a building. The concrete encased electrode provides a large surface area in contact with the earth, resulting in a low resistance to ground. It is an effective grounding electrode, particularly in areas with high soil resistivity. The requirements for concrete encased electrodes are specified in NEC Section 250.52A3. Ground rings are another type of grounding electrode that consists of a bare copper conductor buried in a ring around the perimeter of a building. Ground rings provide a continuous grounding path around the building, improving the overall effectiveness of the grounding system. They are particularly useful for large buildings or facilities with extensive underground metallic piping. The requirements for ground rings are specified in NEC Section 250.52 Rod and pipe electrodes are the most common type of grounding electrode. They consist of metal rod or pipes driven into the ground. Rod and pipe electrodes are typically made of copper, galvanized steel, or stainless steel. The minimum length and diameter of rod and pipe electrodes are specified in NEC Section 250.52. Multiple rod or pipe electrodes may be required to achieve the desired resistance to ground. Plate electrodes are another type of grounding electrode that consists of a metal plate buried in the ground. Plate electrodes provide a large surface area in contact with the earth, resulting in a low resistance to ground. They are typically made of copper or galvanized steel. The minimum size and thickness of plate electrodes are specified in NEC section 250.52-6. Selecting the appropriate type of grounding electrode depends on several factors, including soil conditions, available space, and local code requirements. Soil resistivity is a measure of the resistance of the soil to the flow of electrical current. Low soil resistivity is desirable for effective grounding. Soil resistivity varies depending on the type of soil, moisture content, and temperature. Soil testing should be performed to determine the soil resistivity at the site. In areas with high soil resistivity, it may be necessary to use multiple grounding electrodes or to improve the soil conductivity by adding ground enhancement materials. The available space for installation may limit the type of grounding electrode that can be used. For example, a concrete-encased electrode may not be feasible if the building does not have a concrete footing or foundation. In such cases, rod or pipe electrodes may be the best option. Local code requirements also play a role in selecting the appropriate type of grounding electrode. The NEC specifies the types of grounding electrodes that are permitted, but local jurisdictions may have additional requirements. It is important to check with the local electrical inspector for any specific requirements in the area. Installing grounding electrodes involves driving rods or pipes into the ground, burying plates or rings, or encasing conductors in concrete. The installation should be performed in accordance with the NEC and other applicable codes and standards. Proper installation is essential for ensuring the effectiveness of the grounding system. When driving rod or pipe electrodes into the ground, it is important to avoid damaging underground utilities. The location of underground utilities can be determined by contacting the local one-call center. The electrode should be driven to the required depth and spaced according to the NEC requirements. When burying plate or ring electrodes, the soil should be compacted around the electrode to ensure good contact. The electrode should be buried at the required depth and spaced according to the NEC requirements. When encasing conductors in concrete, the concrete should be thoroughly mixed and poured to ensure that the conductor is completely encased. The concrete should be allowed to cure before connecting the conductor to the grounding system. Connecting grounding electrodes involves connecting the grounding electrode conductor to the grounding electrode. The connection should be made using approved connectors and methods. Proper connections are essential for ensuring a low impedance path for fault currents. The grounding electrode conductor should be sized according to the NEC requirements. The connection should be made in a way that minimizes corrosion and ensures a reliable electrical connection. The connection should be protected from physical damage. Ground resistance testing is a critical step in verifying the effectiveness of the grounding system. Ground resistance testing measures the resistance of the grounding electrode to ground. The resistance should be below the maximum allowable value specified in the NEC. If the resistance is too high, additional grounding electrodes may be required. Ground resistance testing should be performed using approved methods and equipment. The results of the ground resistance test should be documented and kept on file. Ground enhancement materials can be used to improve the conductivity of the soil and lower the resistance of the grounding electrode to ground. Ground enhancement materials are typically made of bentonite clay, gypsum, or other materials that absorb moisture and improve the soil conductivity. Ground enhancement material should be installed according to the manufacturer's instructions. They should be placed around the grounding electrode to improve its effectiveness. Ground enhancement materials can be particularly useful in areas with high soil resistivity. Ongoing maintenance of grounding electrode systems is essential for ensuring their continued effectiveness. Grounding electrodes and conductors should be inspected periodically for corrosion, damage, or loose connections. Ground resistance testing should be performed regularly to verify that the grounding system meets the code requirements. Any deficiencies should be promptly corrected to maintain the integrity of the grounding system and ensure electrical safety. Maintaining proper documentation of the grounding electrode system, including records of inspections, tests, and repairs, is important. This documentation can be helpful for troubleshooting problems, verifying compliance with code requirements, and demonstrating due diligence in maintaining a safe electrical system. Documentation should include the type and location of grounding electrodes, the size and routing of grounding electrode conductors, and the results of ground resistance tests. In summary, grounding electrode systems are a critical component of electrical safety. They protect people and equipment from electrical hazards by providing a low-impedance path for fault currents, stabilizing voltage, and dissipating static electricity. Proper design, installation, and maintenance of grounding electrode systems are essential for ensuring electrical safety and compliance with code requirements. Regularly inspect and test grounding systems to ensure they are functioning properly. Promptly address any deficiencies to maintain the integrity of the grounding system and protect against electrical hazards. Always consult with a qualified electrician or electrical engineer for assistance with grounding electrode systems.